Okay, welcome back. We're now going to continue that theory part, and we're going to talk about the vertical motion of the transverse wave. Imagine this transverse wave is moving to the right. We already stated that yx of t is a sine kx minus vt plus phi. Imagine now I hang at the x equal to 0, I hang a mass m. I want to know what its motion is going to look like. Well, as this wave is propagating this way, the interesting thing about the transverse wave is that the propagation of the energy of the wave is to the right, but the actual motion of an object on the wave, if you put an object, it actually just propagates up and down. It doesn't actually move. So a wave is actually the transfer of energy without actual transfer of motion of an object. Okay? You're not actually transferring objects this way, but you're transferring energy to the right. Okay? So what will happen is that simply this object will bob up and down, right? Because as the wave comes this way, right, the object moves up and down like this. Imagine slightly second later, what is this wave going to look like? Okay, this one will come over here, right? So this portion of the wave here will go over there. This portion will go over there, right? This one will move over there. Right? So the wave, we already mentioned, the wave is going to look something like this, right? It goes like this. So the wave is moving to the right. Well, what happens to the object in blue? The object in blue now is sitting down here. You see? Because it was tied at the position x is 0, it's going to remain at the position x is 0. So it's just going to go down. And then when when the wave keeps traveling, then it's going to go back up, then it's going to go back up, then it's going to go back down, and then so on. It's going to just bob up and down, right? So how can we determine that motion? Well, if we take the derivative of y with respect to t, right, that will tell us how fast the position y is changing. That's called Vy. The velocity Vy is partial y, partial t. And it gives you meters per second. It tells you how fast this mass here bobs up and down, right? So if we take the derivative, what are we going to get with respect to t? A, and then if we take the derivative with respect to t, you're going to get this k, v is going to come out, but it's going to come out as a negative, right? So it's going to come out negative kv, right? And then the derivative of sine is cosine kx minus vt plus phi. So the v sub y is negative akv cosine kx minus vt plus phi, right? So if we try this out here, let's see what's going to happen. Go back to the example that I did, the very first example, where my phi was 0, my k was 1, and omega was 1, right? So phi is 0, k is 1, omega is 1. So what would my equation be? Y of x of t would be, well, the amplitude was also 1, right? So it would just be sine of 1, 1, and the velocity would also be 1, right? So it'll just be sine of x minus t like that, right? And so now, what would the v sub y be? V sub y, well, if a is 1, k is 1, v is 1, it's just negative 1 times cosine, right? Negative cosine, and then this is 1, and this is 1, so x minus t. Okay, so what would v sub y be at exactly the origin? Because that's where I've hung the mass, right? I've hung the mass at x equal to 0. So when x is 0, at t equals to 0, right? At t equals to 0, y of 0, 0, right? So y of 0, 0 gives you 0. So that means the object starts out at the origin, right here. Right? What's v sub y at 0, 0? Right? V sub y at 0, 0. Negative cosine 0 minus 0, negative cosine of 0, well, what does that give you? Negative 1. Negative 1 meter per second. That means initially, right away, when you hang this thing, it's already moving down. And that's what I just said earlier, just by logically deducing, right? Because the wave is moving this way, it's going to start moving down, right away down, right? What's going to happen at t equals 2 pi over 2 seconds, right? So at t equals to pi over 2 seconds, what's going to happen? Well, then you can see the y of 0 pi over 2. I'm interested now only at x equals 0, what's happening, right? At pi over 2 seconds. So then you're going to have here 0 sine of negative pi over 2, right? Sine of negative pi over 2, which we already know is negative 1, right? The wave is going to be down here. What's going to be the velocity of the wave? Right? V sub y at 0 pi over 2 is going to be, then you're going to put here negative cosine, and then you're going to put here 0 minus pi over 2. Right? So what do you get here? Negative cosine of negative pi over 2. Well, cosine of negative pi over 2 is 0. So that means at pi over 2 seconds, the object is down here and it's momentarily, for a split second, not moving, right? How about at pi seconds, right? So now you can kind of see the generalization. Okay, let me just write this equation, the general equation for V sub y over here. Negative AKV cosine of kx minus vt plus phi, right? So then at t equals to pi seconds, then you're going to get what? Well, y is going to go back to the origin, right? Y of 0 pi over 2, you're going to get sine of 0 minus pi over 2. Well, you're going to get y of 0 pi, so that's going to be sine of 0 minus pi. Which is going to be sine of negative pi, which is 0. That means the object has gone from pi over 2 seconds, it went down, then pi seconds, it went back here, right? And then what happened? What's the V sub y? V sub y at 0 pi is negative, right? Cosine, and then here it's going to be 0, right? Minus, and then V was 1, right? So it's just going to be pi seconds. So Vy 0 pi, negative cosine of negative pi. Well, cosine of negative pi is negative 1, right? Cosine of negative pi is negative 1. Negative of negative 1 is 1 meter per second. So what does that mean? The object goes down first, then in pi seconds it goes up. Now it's on the way up. You see? Now the object is hanging like this, and it's on the way up. Right? At 3 pi over 2 seconds, it's going to go all the way up here. It's going to be hanging over there. And then at 2 pi seconds, it's going to be back to where it started. So in other words, our equation is doing a good job of predicting that it's moving down first, and then up, and then down. So a wave that's moving to the right, right? An object at the origin, if the phase angle is 0, the object first starts moving down, then it goes up, then it goes down. Of course, all of these changes, if we change the phase angle and we change the starting position of the object could be hanging here. The object could be hanging here. The object could be hanging some random place, right? So it's not always true that it first moves down, then up, then down. So it all depends on where it's hung, and it all depends on the phase angle that's given to the wave, okay? But at least for our case, it is working, okay? How about if you take the derivative of that again? Y partial t, right? And then you're going to get the derivative of cosine is negative sine, so you're going to get another negative coming out. So AKB, right? Negative sign. But then you're going to get another negative coming out from here. Then you're going to get here negative KV, and then sine of KX minus VT plus phi. So A sub y. So you see two negatives came out. The derivative of cosine was negative sine, right? And that get rid of this one. So it became AKV, right? Then another negative came out from here, negative KV. So now it's going to be negative A K squared V squared sine of Kx minus Vt plus phi. Right? So what does that mean? When I put here 0, 0, you're going to get what? A sub y at 0, 0. You're going to get here a negative sine of 0, which is going to be just 0. So right at the beginning, the object is not accelerating, right? But it's moving down, right? It's moving down, but its acceleration is 0. So it's very similar to the motion of a block on a spring, right? Think of it like this. X equal to 0, right? So blocks motion, and it could even be perpendicular motion or horizontal motion. It doesn't matter. At the equilibrium point, the velocity is equal to the maximum velocity, but it could be moving to the right or it could be moving to the left. You see? At the end points, the velocity is 0. The acceleration is equal to what? It's going to be negative because the spring is pulling back on the block. So the acceleration is negative A max. That's the maximum acceleration, right? Then when the spring comes back, passes the equilibrium point, now the velocity is going to be negative, right? Then the acceleration is going to be 0. So at the middle, the acceleration is 0. Why? Because the spring exerts no force on the block at the equilibrium point. And since F equals negative Kx, which equals ma, at the equilibrium point, x is 0, the acceleration is 0. So you see at the equilibrium points, whenever the object is going up and down, at the equilibrium points, it's kind of like a block being at the equilibrium point of a spring. Okay? The spring exerts no force, the acceleration is 0. So whenever the object is here, here, and then when this object moves down here, it should not be accelerating. At the two end points, it should have the maximum acceleration, right? So over here, when the block is here, it has the most negative acceleration because it's going to be down. And then over here, when the spring is most compressed, right here, you see, then the spring is exerting a force this way, right? A is equal to A max. This one is A is negative A max, right? So this one reaches the most positive acceleration because now the block is going to start heading this way, and then the velocity is going to be 0. And just focus on the object here, like this, hanging from here. At that position, the acceleration is going to be 0. The velocity is going to equal negative V max, right? And then it's going to start moving down until it gets to the most bottom position. The velocity is going to equal 0. A is going to equal to positive A max. It's going to start moving back up. Just like this block is starting to move back to the equilibrium. And that's what this equation should give you. It should give you the maximum acceleration when it goes down to the bottom. It should be positive, right? And then it should move back up. It should move back up, right, to the equilibrium. Now it's going to go back this way here. When it's over here. Now, when it reaches back to equilibrium, what's going to happen? The acceleration is going to be 0. V is going to equal positive V max. It's going to be moving positive. So that means it's like the block moving this way. And then when it reaches the top position here, A is going to equal negative A max. Then it's going to be accelerating back. And then the same thing. This mass, when it goes up here, it's going to be accelerating down. You see? And then what? and then you have here, the velocity here should be 0 at the top. So model it like a block on a spring, and you will kind of understand the motion of an object hanging from a transverse wave. Okay? What's the period of the motion? How long will it take? Remember, for a block and a spring, what did we say? We said omega is equal to 2 pi over t, right? T is equal to 2 pi over omega. Okay, in the case of the spring, omega was square root of k over m. And then we just put this over here, 2 pi square root of m over k. So that was the period of the motion of an object hanging from the spring. We're assuming the mass of the spring is negligible. So how about in this case? What's the period of the motion? Okay, well, in our case, the period of the motion is simply the omega that the wave is propagating at, right? So omega is 2 pi over t. T is simply 2 pi over omega. In our case, the omega was 1 radian per second, so the period is going to be 2 pi seconds, right? 1 radian per second. This is radians, radian cancel, 2 pi seconds. So what will that mean? Object will go down in pi over 2 seconds, then go back up pi seconds, then go over here 3 pi over 2 seconds, and then be back down to where it began in 2 pi seconds. So when it made the whole journey in 2 pi seconds, right? We can try to change the values. Okay, remember the second wave that we tried was what? We tried k is equal to 2 rads per second, rads per meter. Omega is 1 rad per second. And then we noticed that that one, the velocity of the wave would be 0.5 meter per second. So what would be the wavelength of that wave? Well, the wavelength of the wave is going to be shortened, right? We noticed that in the previous theory lecture. Lambda was equal to pi meters. What's going to happen to the period? How long will it take it to go back up and down? The period is not changing because I kept the omega as 1 radian per second. So the period is still going to be 2 pi seconds. So what are the equations of its velocity? Y, Vy, and Ay. Okay? So y of xt, A is 1, sine of k was equal to what? 2. And then the velocity was 1/2 plus phi. Well, phi was 0 in our case. This is one way of writing it, but you don't necessarily have to write 2x minus ½ t. You could also just simply write, you could distribute the 2 in and then just write it simpler as 2x minus t. Either way is okay. But this way you can kind of quickly see that the velocity of the wave is 0.5 meter per second. Whereas this one you can't really see quickly. Okay? Then the Vy x of t is the derivative of this, right? Negative AKV, well, A is 1, right? So negative 1, and then K is equal to what? 2, right? And then V is equal to 1/2. Okay, cosine, then you're going to have here 2x minus 1/2 t. So the general equation for V sub y, negative cosine 2x minus 1/2 t. Okay? So what does that mean? The velocity in the y direction did not change, the amplitude, you see? Because I've basically doubled the k, right? But I've halved the v. So v is equal to omega over k, right? kv is equal to what? Omega. So we could kind of re-express these equations as kv, we could write it either as kv or we could write it as omega. Right? What is this? K squared v squared. We could write this as omega squared. So if I keep the omega of the wave the same, it doesn't matter what I do to the k. Right? So the v sub y doesn't change. It still stays negative cosine 2x minus ½ t. And then a sub y is going to equal negative, and then this is still going to be omega, which is 1, sine of 2x minus a half t. In other words, the up and down motion of this wave is exactly the same as the wave that has k is 1, except the one difference that the wave is just shorter. But in terms of the Vy and the Ay, their amplitudes haven't changed, and the period of the motion hasn't changed in the vertical direction. The period is 2 pi over omega, so it's still 2 pi seconds. So it still takes the same amount of seconds for the object to go up and back down. Now what if I change this way? I say k is 1, omega is 2 rads per second. What's going to happen to the v? What's going to happen to the wavelength? What's going to happen to the period? And how do these equations change? Okay? When k is 1, omega is 2, velocity will be what? Velocity equals to omega over k, 2 over 1, 2 meters per second. Oh, now this wave travels faster, actually. It travels faster, twice as fast. Okay? What happens to its wavelength? What's the wavelength of the wave? Well, the wavelength depends on the k, right? So if the k goes back to being 1, the wavelength of the wave is 2 pi meters. So the wavelength is still the very original wavelength, which was the 2 pi meters. But what happens to the period of the motion in the vertical direction? Now it gets cut in half, right? Why? Because now it's 2 pi over omega, and then omega is 2 pi seconds, right? So now the wave is traveling faster this way. Not only, it's not traveling slower, it's traveling faster this way. So not only is it traveling faster this way, it's traveling up and down twice as fast. So twice as fast this way, and then twice as fast this way. Whereas when the k was 2 and the omega was 1, it travels half as fast this way, up and down, travels the same amount. The equation is going to change. So here it's going to be y sine of, this one is going to be 1, and then omega is going to be 2, right? So it's going to be, we put here 1, x minus 2t. Okay, so instead of 2x minus t, it's x minus 2t. Right? So then negative 2 cosine of x minus 2t. Right? So the velocity that it's going down is double now. Right? When x equals to 0, when t equals to 0, right? You got cosine of 0, which is 1. It's already moving down at negative 2 meters per second, downwards. Its velocity to the right is 2 meters per second. So this is doubled and this is doubled. You see? How about the a sub y? A sub y, x of t, is equal to partial vy partial t. So we take its derivative again with respect to t. So derivative of cosine comes out to be negative sine, so 2 sine of x minus 2t. And then the derivative of the inside is going to be another negative 2. So now it's going to be a sub y, x of t, negative 4 sine of x minus 2t. Right? What happens now? When x equal to 0, t equal to 0, you got sine of 0 minus 0, so you got sine of 0, which is 0. So at the origin, it's not accelerating again, right? But the acceleration, the maximum value of the acceleration, instead of being 1, it's now 4. You see here? K squared, v squared, omega squared. So if I've doubled the omega, I've quadrupled the maximum acceleration. So there's a lot more force, and this thing is going up and down twice as quick, and at the ends, it's accelerating 4 times as fast. So now we have an idea of how changing the k, what it does, what changing the omega does, and then how it affects the v's, how it affects the y, vy, ay, and we can also compare that to the motion of a block on a spring. So now we'll actually do an example and see how we can use this in an actual example. Thank you.